So, good morning, everyone. My name is Neeraj Tiwari. I'm from Electronics and Communication Department, Technocrats TID Group. So, today I'm going to lecture it on electromagnetic theory. Topic is boundary condition. In the last class, we have seen boundary conditions in dielectric 1 and dielectric 2 medium. Now, today we are going to see boundary conditions for it's a conductor and dielectric medium. So boundary condition, we'll see conductor dielectric medium. In the last class, we have seen dielectric 1 and dielectric 2. Now we are going to see conductor and dielectric medium. So in conductor and dielectric medium, first of all, you need to keep in mind that electric field cannot sustain in conducting material. So here I will talk about perfect conductor like silver, copper. Conductor means conductivity. Conductivity goes around infinite, and resistivity goes around it's a zero. So in case of conductor, perfect conductor, I would say conductivity goes to infinite. So as you can see here, it's a conductivity. Conductivity means sigma goes to infinite, and here you can see resistivity, which is goes around zero. So this is the basic definition of a perfect conductor. So as we know that electrical intensity cannot contain, or you can say doesn't contain inside the conducting material. This is a punchline you can have in your mind, or you can say commit to memory. So basically, here we will talk about a perfect conductor. Perfect conductor, that means it's a silver and copper. That means conductivity goes around infinite and resistivity goes to zero. So how we will determine the boundary conditions for conducting and dielectric medium? Here you can see in this diagram. In this diagram, you can see it's a diagram and it's a B diagram. It's a diagram. In this diagram, we will use E dot dl is equals to 0, as I told you in the previous class. E dot dl is equals to 0, which is basically a Maxwell first equation. So we have to apply Maxwell first equation, which is E dot dl is equals to 0 here. So how we will apply Maxwell first equation here? See, here you can see it's a boundary. It's a thin line. You can see it's a boundary. It's a we can assume as a boundary, and across the boundary, this is the medium 1, and this is the downside. In downside, you can see it's a medium 2. So in medium 1, we are assumed as a dielectric medium, and in medium 2, we are assuming as a conducting material. I would say a perfect conductor. A perfect conductor, that means E is equals to 0 inside the conductor. E is equals to 0 inside the conductor. We have to keep in mind E is equals to 0 inside the perfect conductor. So as I told you, how we will apply Maxwell first equation in this boundary, or you can say across the boundary. In the same way, you have to draw the tangential component, normal component, then you will get resultant. The same path we will follow in this diagram. So here you can see it's a boundary. It's a boundary. You can see. It's a boundary. You can see now clearly. You can see it's a ET. It's a tangential component. So you have to draw a tangential component of electric field intensity, and this is En. En is a normal component of electric field intensity, and the resultant of both tangential and normal would be E, which is called electric field intensity in the medium 1. And now how you can define medium? Medium you can define by epsilon. Epsilon, it's a permittivity, or permittivity, you can define, you can write a formula by if epsilon is equals to epsilon naught into epsilon r. And as you know that epsilon r is equals to 1 for free space, but here is a dielectric, so here would be a different value. uh, Now the second, if you if you uh, if you see here, it's a b c d. What is this? It's a closed path. As I told you, E dot dl is equals to 0, as Maxwell first equation applied in a closed path. That's why I have draw a closed path. E dot dl is equals to 0. So in this diagram, as you can see, d to c, d to c, as we move from d to c, C to B, and A to B, and A to D. So this is the closed path. So as we move from A to B, the length is del W. As we move from B to C, the height is del H, and again we move from again if we move from C to D, again the length would be same, which is del W. And again if we move from D to A, the height would be same, del H. So again, so we have to apply Maxwell first equation in this diagram. So how we will apply Maxwell first equation? Let's see the equation. How I can write. See, it's a equation. In the same fashion, we have write this equation as we have done in the first class. So here you can see 0. Why came 0 here? E dot dl is equals to 0. So that 0 is came here, and now it's a equal to sign. Now here you can see 0 dot del w. Why 0 and del w came here? 0 and del w came here. E is equals to 0 means E is equals to 0, and if we moving from tangential component, del w is what? Nothing. That's why del w into what is electrical intensity inside the conductor, 0. So that's why 0 dot del w. Again we move from B to C. If we move from B to C, it's a tangential component, and in tangential component will what? You are moving again 0. If you are moving, B to C, so before this line, or you can say before this boundary, what will be the length of this line? It is a del H by 2. So what will happen again? Plus 0 into del H by 2. So clearly you can see 0 into del H by 2. So clearly you can see here 0 into del H by 2. In the same way, En into del H by 2 minus Et into del W minus En into del H by 2 minus 0 into del H by 2. Similarly, you can apply and you can get this kind of equation, which is a and finally you have to put del H tends to 0 because it's a thin line, and here we can assume it's a height which is tends to, or you can say goes to near about 0. So if you simplify this equation 5.666, then you will get Et is equals to 0. That means a tangential component of electrical intensity would be 0. So I am taking this is a 5.67 equation number. It's a 5.67. Et is equals to 0 means tangential component of electrical intensity is 0. So again, again if Tn Ut is equals to 0. Now apply the Maxwell second equation, which is what is Maxwell's second equation? It is derived from the Gauss law. What Gauss law says, total flux passing through the closed surface is equal to the total charge present in the closed surface. That means d dot ds is equals to q enclosed. Integration of d dot ds is equals to q enclosed, where q enclosed is what? The total charge present in the closed surface, that is called Q enclosed. So in the same way, as we know that what is the relationship between D and A, which we know that it's a D. D is equals to epsilon E, which is equals to 0, and inside the conductor. So normally you can write as D and so inside the conductor you can write as D is equals to epsilon 0 and epsilon E is equals to 0. Now finally, if you write for the normal component of electric flux density, then equation you will get dn is equals to del q upon del s is equals to rho s. As we know that dn is equals to rho s, because as we know that the charges are inside the charges are 0. Volume charge density is 0, but the surface charge density will exist there. I would say, in perfect conductor, charges are in the surface area. That means there is a surface charge area, that means surface charge will exist there. That's why I'm saying here dn is equals to del q upon del s, because charges are there. So that's why I'm writing here dn is equals to rho s. I'm assuming as a 5.69 equation. So finally, you can write that dn is equals to rho s. So what conclusion we have got from the boundary conditions formula? First one is no electric field may exist within a conductor. That's true. No electric field can exist within a conductor, or you can say inside the conductor. That means I would say E is equals to 0. If you can say E is equals to 0, that means it would be del V. Del V is equals to 0. Del V means what? Del V, it's a volume charge density. Now, of course, if you are saying E is equals to 0, that means it would be del V is equals to 0, because del V is the volume charge density. Now, if you're saying del V is equals to 0, now the another formula remind another formula, which is E is equals to minus of gradient V, so is equals to 0. So in this formula we can see that there is no potential difference. There is no potential difference between inside the conductor, or that means I would say perfect conductor would behave like a equipotential body, behaves like a equipotential body. In another words, we can say that conductor is an equipotential body. Now the third point can be concluded as as we have derived dt is equals to 0. So as we know that d is equals to epsilon into E, so so epsilon you can write as epsilon naught into epsilon r. So equation becomes d is equals to epsilon naught into epsilon r into ut, which is equal to 0. In the same case, for the normal component of electric flux density, what would be, epsilon naught into epsilon r into En is equals to rho s. So clearly we can see tangential component of electric flux density would be 0, and normal component of electric flux density would be rho s. Rho s is a surface charge density. So an important conclusion we have derived from this equation, as we know that E is equals to 0. That means electric field intensity is 0 inside a conductor. Now this third case in which you have to derive a formula by using boundary conditions. Third one is conductor and free space boundary condition. So simply you can see the diagram of conductor free space boundary condition. This is the diagram of conductor free space boundary condition. In this diagram you can see here is the conductor. The downside, in this figure you can see downside, the downside is the conductor and upper side is a free space. In free space you can write as epsilon, so epsilon is equal to epsilon naught into epsilon r. So in case of free space, undoubtedly you can write as epsilon r is equals to 1 for free space. And the same formula and the same and formula will be same, and except epsilon r would be 1. So from the previous formula you have to put epsilon in place of epsilon r, you have to put 1, then you will get finally 5.72, like dt is equals to, in in place of epsilon r would be 1, so epsilon naught into et is equals to 0, and dn is equals to epsilon naught into en is equals to rho s. So this is very simple to evaluate boundary conditions for conductor and free space boundary conditions. You have to keep in mind that in case of free space you have to put epsilon r is equals to 1, in case of conductor and dielectric medium. So what formula we have derived from the previous section? It's a conductor free space, sorry, conductor dielectric boundary conditions. So in conductor dielectric boundary conditions, now you have to put for the free space epsilon r is equals to 1, and the same formula will be applicable for the conductor free space boundary conditions. So this is the one of the important formula. Dt is equals to 0 and dn is equals to rho s for the same for the conductor free space boundary condition. Okay. Now, okay, thank you class.